So this particular discussion, we're going to be talking about electronic and atomic domains. Okay, and what this does is it has to do with the determination of shape around a central atom. Okay, not a whole molecule for the most part, but around a particular central atom, and see what the shape is around there. Okay, we can start with the things that are a little bit basic. And the first thing you have to understand is what's causing the shape. Okay, so we have to talk about valence shell electrons. We can't talk about inner core electrons because they're kind of covered by everything that's around there, right? You don't look at the center of a flower and say, oh, well, that's determining the shape. No, it's the petals around the flower that kind of make the shape, right? Okay, so when I look at that outer shell, I'm looking at the valence shell, okay? Valence shell electrons. Now, when I'm talking about electron pairs, I'm talking about things that have lone pairs. Yes, good. And I'm talking about things that have bonds. Okay, so electron pairs and bonds are going to be important there. And then they get over here to repulsion. Okay, why do they repulse? What's the charge in an electron? That's right, negative. And if I have negative electrons and they get together closer and closer in their valence shells, what are they going to do? Repel. So valence shell electrons are going to repel. So the shapes are determined by something called valence shell electron pair repulsion, and we call that VSEPR. Okay, and the VSEPR shapes are what determines basically what atom or what atomic shapes are going to be around a particular center. So let's start with something simple. Okay, and I'm going to look at hydrogen. Okay, hydrogen. There's only one pair of electrons between all the hydrogens. So what I do is I pick one of the atoms. And what I'm going to do is I'm going to pick one of these hydrogens. I pick that hydrogen. Okay? Now how many electrons are around it? It's just that one bond, right? So I've only got one electronic domain here. Okay? The electronic domain is the bond. So one bond is my electronic domain. Okay? But what's it bound to? It's bound to an atom. So since it's bound to an atom, it's going to be an atomic domain. So one bond. Okay? Since the bonds are the same, I don't have anything else that's going to sort of perturb my shape. The shape is going to be pretty straightforward. So since the electronic domains are one, and I'm going to erase this and say, or actually I could keep it there, one bond. This one has one bond. Since the atomic domain is one bond, I've got two of these things together. If I have 2 points in space, it's going to define what? A line, right? So the shape of this guy is a line. So this is linear. Linear shape. Okay? Good. Let's go to something a little bit more complex, and I'm going to move to something that is BF3. Okay? Boron trifluoride. And I'm only looking at the central atom here in boron. So if I look at boron trifluoride, if I construct this using Lewis dots, the boron has 3 dots, okay? And I'm going to get fluorine times 3. So the fluorine bond is going to stick to all the single electrons, okay? So if I look at the shape that I get out of this, okay, by Lewis dot structures, I get something that looks like this. Okay? Now that's all well and good. I've got something that's a Lewis dot structure, and by Lewis dot structures that's fine. But does this accurately represent the shape of BF3? Okay? The answer is no, it doesn't. Why not? Well, if we're talking about electronic repulsion here, we've got to maximize the distance between all of the electrons. They're pushing away to a certain point where you get sort of electrostatic repulsion equilibrium. Okay? So these things are pushing away from each other to a certain point. Okay, what I'm going to get is a boron here with a fluorine and a fluorine and a fluorine. And all of the angles have to be the same. So what is the angle here? Well, if you think about that this kind of looks like a triangle, what's the bond angle from the radius or the central point of a triangle? 120 degrees. Good. Okay, so that's 120 degrees away from each other. So for BF3 How many electronic domains do I have? I have 3 bonds. Okay? I have no lone pairs around the boron. Okay? My atomic domains are 3. Okay? I only count the bonds here for BF3. So what's the shape? You're thinking triangle. You're right. So this is triangle. But we're scientists, and we like to sound nerdy, so we call it trigonal. Okay? What's underneath that? What? What do you mean underneath that? It's trigonal. But it's a special kind of trigonal. Trigonals can be deformed in space, right? Okay? And if they're deformed in space, they're going to come up with a different shape. So we have to say that there's a certain dimensionality here. The dimensionality, it's flat. It's a nerdy way of saying flat. Dimensionality is a trigonal planar structure. It's a flat triangle, right? Okay. So trigonal planar, flat triangle is what the shape of BF3 is. Okay? Now what I want to do is I want to point out what's happening with the fluorine. Okay, what's happening with the fluorine? If I look at the electronic domains here, I've got 1 bond. But the fluorine also has what? 3 lone pairs. All right. Now there's something important that we have to recognize here. Because I've got 1 bond and 3 lone pairs, I've got a structure that is going to be different than if I've got just 3 bonds and 3 electronic domains. I've got 4 electronic domains. So that means the overall shape is going to be different. Okay? But I've only got 1 bond. The thing that determines the shape here, because I've only got 1 bond, I'm still going to have a linear structure. The electronic domain shape is going to be something else, though. Right? It's got 4 points in space. I want you to think about that for a second, because I'm going to go into something that does have 4 points in space. And it's something we're all familiar with, and that is methane, CH4, natural gas. Cow farts, right? So I've got cow farts here, and if I draw this out in a Lewis structure, it looks like that. Okay? But the bond angle that I've got drawn here is 90 degrees. And that would work great if molecules were 2-dimensional constructs, if everything was flat. Guess what? It's not flat. There's a 3-dimension to it, 3rd dimension. Okay? If these things push out a little bit more, if I push this hydrogen down, what happens is that this one kind of pushes out at the board at you. So that becomes a wedge, and the wedge represents the hydrogen coming at you. Now if I look at this other hydrogen, this one is kind of going away from us. So now a CH4 is properly represented in space. It's not a 90-degree angle, it's about 20 degrees more. It's about 109.5 degrees as far as the bond angle there. Now what is this shape? If I've got this shape that is a central carbon and 4 points around the center of it. So here's my central carbon. Now look at H there, H over here, H in the back. Now look at that shape. What's happening there? Does the central carbon actually add to the shape in this case? No. Just like it did with boron, boron was not adding to the shape because it's confined within the overall shape of the molecule. So it's not included as a point. So if I erase these hydrogens and just put little points where they are and try out the shape, I've got something that kind of looks like a pyramid. Right, with a central point. Everything is equilateral there. As a result, because of that equilateral nature, this thing is called a tetrahedron. So my overall shape, I've got 4 bonds. Okay, and I've also got 4 bonds in the atomic domains. Remember, we only count bonds, not lone pairs, in with the atomic domains. The shape is considered tetrahedral. So now I'm going to go back and look at this fluorine. The electronic domain here had what shape? What shape was it? That's right. It's a tetrahedron. Because I've got 1 plus 3. So if my electronic domains are 4, it's got to maintain the same shape. Because electrons are just going to repel as much as they can. If I've only got 4 points, it defines the shape. The electronic domain here is 4 around the fluorine. Even though it's giving me a linear structure, it's got 4. Okay? All right, so this is a tetrahedral electronic domain. Okay. So let's move into molecules that have central atoms that have lone pairs and see how that influences the shape. Okay?